Right. And here's the second part of chapter 3. The topics are membrane function, which is mostly how things get across it, and cell division. Methods for getting a substance across the membrane can be put into two categories based on whether the cell has to spend energy to move the substance. If it doesn't have to spend energy, the substances just move because they're bouncing around. That's a passive process. These include simple and facilitated diffusion and osmosis. Active processes, the cell has to spend energy to make them happen. These are active transport and vesicular transport. Can you guess what kind of organelle vesicular transport is going to use? Vesicles. Diffusion happens because substances spread out over time. You may start a substance in one place. Let's say you put a little block of salt in a beaker. It starts to dissolve and spread out from there. And until it's equally distributed, you have a difference in how concentrated it is where. That's called a concentration gradient. You've seen these signs where it's hilly. Sometimes there's a number at the bottom to tell you how steep the hill is. That's called a gradient on the road. A concentration gradient is similar in that it's easier to go downhill or from high concentration to low concentration, or where there's more of the stuff to where there's less of it. Diffusion always goes from high concentration to low. We call that going down the concentration gradient or with the concentration gradient. If we were going the other way, it would be against the concentration gradient. That's going to require energy. Simple diffusion is just a substance spreading out to fill the space. So our little sugar cube here starts to break up. It's still more concentrated where it was, but it's reaching out to the other places until finally it's evenly distributed, and then it's done diffusing. Now, for something to get across the cell membrane by simple diffusion, it needs to be something that isn't blocked by the phospholipids. So it needs to be either lipid soluble, such as steroid hormones, or a gas. So oxygen and CO2 can go straight through the cell membrane by simple diffusion. A lot of anesthetics that are gases can also go the same way. Facilitated diffusion is still things spreading out, but now it's things that can't just go straight through the cell membrane. They need to find a transport protein in order to get across. So here's our substance in blue. It wants to go into the cell because it's less concentrated there. But it's hydrophilic, so it bounces back off the membrane. Your transport protein, channel or carrier, can let the substance go through. Because it has to get to the right place to get in, facilitated diffusion is often slower than simple diffusion. It's going to depend on just how many transport proteins there are compared to how much stuff is trying to cross. So you could think of it as, say there's a soccer field. To lipids that can do simple diffusion, the cell membrane is just the line at the edge of the field, and they can just go across it, it doesn't stop them. But to ions and other small hydrophilic things, the cell membrane is a fence, and it can't climb over, it has to find a gate to get through. There's two main categories of transport proteins, channels and carriers. Channels are like an open door. The substance can get through them from one side of the membrane to the other. They'll always follow their concentration gradient. These can only be for very small substances because the channel is set up so that only a certain thing goes through, partially based on size, but sometimes charge. Like if you wanted to let cations through, you might have a channel that's negatively charged, so they'd be attracted to it. But anything negative would be repelled by it. For anything larger, having an open channel, you'd have too big a space where other things could just go through whenever they wanted to. So for larger things like glucose, we use carriers. These are more like airlocks. Let's use half this cell. A carrier is only open to one side of the membrane. The substance goes into the carrier, and then the carrier changes shape to open to the other side of the membrane and let the substance out. So for something that's too big to just have an open channel, you'll use a carrier. Okay. And this is kind of like, the carrier is for things that need to use the freight elevator. Anybody can just go into the freight elevator unless you've got a key for it. You don't have to be big. Whereas the big things can't go through a little channel, the regular elevator. So here's a channel. We've got our protein in the membrane. The substances are more concentrated here, so they're going through this way. Here's a carrier. Again, the substances are going with their gradient, but it has to go into the carrier, and then the carrier switches positions to let the substance out on the other side. So both of these are facilitated diffusion. The transport protein facilitates or helps the substance get across. There's not actually any sound on this one. Here's our, they're calling that a carrier. So even though it looks like it's open, the substance is going to get in and sit on that spot and then get pushed through. If it were just a regular channel, these little yellow guys would just be able to go right through it instead of having to wait for it to shift.
It's like the pinball machine, or you know, the little flapper thing.
Oh yeah. You could get a lot of different potential shapes for carriers. Like the one they've shown here is the kind of a clam, but it opens on both sides. That one was kind of the pinball paddles. So, questions on simple and facilitated diffusion? Our other passive process is osmosis. Now, in osmosis, only water is the substance moving. So we could call it diffusion of water. But what's weird there is when a solution is more concentrated, it has more solutes, that's where it's actually a lower concentration of water. So the water wants to go toward the area with more solutes. This will happen when the solutes can't move to balance out their concentration. The water wants to at least balance out the overall concentration of solutes. But because the water determines the volume, when the water moves, the volume changes. So over here we have two solutions on sides of a membrane. A is more concentrated with these purple solutes. The solutes can't fit through the membrane, but the water can, because water's actually really tiny. It's only got an atomic weight of 18. 16 for the oxygen, 8 protons, 8 neutrons, and then 1 for each hydrogen. Whereas even a sodium ion is like 23. So the water goes through towards the side with more solutes. And that means this side shrinks, this side grows. So cells are what's called selectively permeable. They let some things cross and not others, based on if that substance can just get through the membrane, the cell is permeable to it. If it has channels and carriers, then how permeable it is based on how many of them it has. So some solutes can't enter. Sometimes a transport protein is only open under certain circumstances, so substance that can enter some of the time can't enter other times. So if the concentration is off, the area that's more concentrated, has more solutes, exerts what's called osmotic pressure that pulls the water towards it. We use 3 terms for solutions based on how their concentration compares to a cell. Now, I'm going to come over here and draw these out. We'll make one of them just water, one of them a little bit a solute, and one of them lots of solute. We use red blood cells to illustrate this because they have this kind of bent shape. They're kind of flattened, so they have more room that they could fill up, so you can see the difference easily. Put a cell in. Now, in this solution, this is isotonic, which means the cell and the solution around it are the same concentration. The water moves around, but it's not specifically pulled into or out of the cell, so you don't get any change in volume. We put a cell over here where there's no solutes. There's always some solutes in the cells. Now the water looks at the cell and goes, "Oh my God, it's so concentrated in there. Let's fix it." So the water goes in, This solution is called hypotonic. Hypo is below, like a hypodermic needle goes under the skin. Here it means lower concentration. You put water into the cell, and it's going to swell. One way to remember this O, think hypotonic, and that's your big fat cell from sucking up the water. Our third one here this solution is more concentrated than the cell, hypertonic. Hyper is above, like a hyperactive kid has more activity.